In this video, we're going to be taking notes on series. A series is the sum of consecutive terms of a sequence. So that means we're just adding up the terms in a sequence. An arithmetic series is the sum of terms in an arithmetic sequence, and a geometric series is the sum of terms in a geometric sequence. So, here's some examples. Number 1, find the sum of the first 5 terms of a sub n equals 6 plus the quantity n minus 1 times 4. So first we want to figure out what are the first 5 terms. Well, to figure them out, I'm going to plug in n equals 1, and I should recognize that this is an arithmetic sequence when I plug into it. So that would equal 6 if I simplified. I could then plug in 2 for n, and when I plug in 2 for n, I'll get 10. If I continue going with this, I plug in a 3, I get 14, plug in a 4, I get 18, and plug in a 5, I get 22. Hopefully we realize that's because the common difference is 4. So this is now a sequence because instead of having commas between the terms, I have, it's a series because instead of having commas between the terms, I have pluses. B says now add them together. That's the sum of the series, and if I literally just took these and added them up, so I can see I add them up on my calculator, I get 70, then 70 is the sum of the series. In number 2, we have a geometric series. So when it's written like this, I can see the sequence and the formula for the sequence. I'm supposed to find the first 8 terms. So I'm going to start out by plugging a 1 in for n to the formula. When I plug in a 1, I get 1 when I simplify. Then I plug in a 2 to get 2. I plug in a 3 to get 4. I plug in a 4 to get 8, and so on. Every time I should recognize what I'm doing is doubling. And I can tell I'm doubling because my common ratio here in the formula was 2. So I can list out all the terms. Again, to find the sum, I'm just going to add them all up. And you could take my word for it, if we added them all together, the sum would be 255. So this is great, but if I want to find a lot of these sums, it would be nice if we had some formulas. So if we scroll down, we'll see some formulas there. In this example, we want to find the sum of the integers from 1 to 16. So we list them all out, 1 plus 2 plus 3 plus 4, all the way up to 16. Now you'll notice if we start grouping them together, if I add 1 and 16 together, the sum of that is 17. If I had added 2 and 15 together, the sum would also be 17. If I added 3 and 14 together, the sum would also be 17, and so on and so on. So each of these pairs are going to add up to 17. So we just need to figure out how many pairs are there. Well, there are 8 pairs. We could count them up, or we could say there were 16 total items. 16 is the number of terms we have. And then we're going to divide that by 2. We're dividing by 2 because that's how many are in a pair. So this brings us to the formula for the sum of an arithmetic series. The sum of an arithmetic series is on your formula sheet. It will be given to you when you take your tests, quizzes, or your SOL. And I've got 2 versions of this formula. I've got the first one, S sub n. S now stands for the sum of the first n terms. So whereas a sub 16 was the 16th term, s sub 16 is the sum of the first 16 terms. And then on the right there we have n over 2, and we multiply that times the quantity of a sub 1 plus a sub n. So a sub 1 is your first term, and this is in essence your last term or your nth term. If we don't know the last term, we can also use this second formula, which doesn't require a sub n. It only requires the first term, the number of terms, and the common difference. The formulas are interchangeable. Both will work in any situation. You might have to work harder to use one or the other though. Okay, so let's look at some examples of trying these. I just rewrote the formulas up on the top of the page. There again is the 2 separate formulas. In number 3, it says find the sum of the integers from 1 through 1,000. We should recognize that the integers are the numbers like 1, 2, 3, 4, so on and so on, up to 1,000. Clearly, I'm not going to want to add all these up on my own, since I know the first term is 1. I know the 1,000th term is 1,000, and I know I have 1,000 terms. I can use that first sum formula. So I'll say the sum of the first 1,000 terms is equal to, and on the top of the formula I have n, the number of terms, which would be 1,000. To always divide by 2 because I'm grouping them together. My first term was 1, and my last term was 1,000. So when I plug into my formula, if I simplify that, I can type it right into my calculator. Be sure when you're typing into your calculator, you're putting your first term in parentheses, and you can see we got 500,500. In example 4, they give us some different information. They give us the first term and the common difference and ask for the sum of the first 10 terms. So this is written S sub 10. Using either formula, I would start out with 10 over 2. If I try to plug into the first formula, I'm going to need to know A sub n, the 10th term. I don't know the 10th term, so in this case, it's better to use the second formula. So using the second formula, I have double the first term, which was 40. Then I have n minus 1, which would be 10 minus 1, times d, my common difference, which is negative 3. And then I can simplify that or plug it into my calculator. So I just have to watch my use of parentheses or do it in little steps following order of operations, but my sum is 265. I'm going to go ahead and do number 5 because it shows the difference between a sequence and a series. So in this one it says you decide you are going to put money in a piggy bank. Each week you are going to insert $3 more than the previous week. The first week you put in $10. So what do we know? The first week we put in $10 means A sub 1 is $10. The fact that you insert $3 more than the previous week each week tells us that our common difference is $3, and that's how we know that this is arithmetic. Part A asks how much money will you insert during the 25th week. So this is only how much you have the 25th week, which would be the 25th term. So I can plug into my formula again from the formula sheet for an arithmetic sequence is A sub n, which is A sub 25, equals A sub 1, and our first term here was 10, plus, then we have n minus 1, so we have 25 minus 1, and we're going to multiply that by our common difference, which was 3. If I typed that into my calculator, I would find that the 25th term was $82. So this means I put $82 in the piggy bank on the 25th week. Part B asks how much money will we have in our account after that deposit. So total amount of money in the piggy bank is the sum. So this would be the sum of the first 25 terms. Well, plugging into our sum formula from above, that's 25 over 2. And then we add to that the first term was 10, and we just found the last term, or the 25th term, which was $82. So if we put all of that together, either in our calculator or add it up, we wind up with $1,150. We also have a geometric series, and to find the sum of a finite means it has an end. Right, there's a specific number of terms. To find the sum of a finite geometric series, we use this formula right here. It also says on the formula sheet that r can't be equal to 1. We should recognize that because that would create division by 0. And it also tells us that r is the common ratio, just like it was in a geometric sequence. So we're not going to derive this formula like we saw the last one because it's a little harder to put together where the parts come from. All right, so let's just use the formula. Number 7 says find the sum of the first 12 powers of 3. So starting with 3 to the first, then 3 to the second would be 9, 3 to the third would be 27, and so on until we got up to 3 to the 12th. I'm not going to worry about what that really is. I'm going to use my sum formula. So plugging in above, the sum of the first 12 terms, Up on the top, the first thing I plug in is a sub 1, so my first term would be 3. Then I have 1 minus the common ratio. Well, my common ratio is what I always multiply by to get the next term, which in this case was 3. The exponent is 12, because that's the number of terms. And on the bottom of the fraction, I have 1 minus the common ratio, which again was 3. I can type this into my calculator exactly where the parentheses are written right now, and I can see that my sum is 797,160. The biggest mistake that you guys make with these is typing them into your calculator wrong, so just be careful with the parentheses. So that's an example where I just gave you some information. I could also give you like this where we have a list, so we'd have to figure out, oh, this is geometric, and what do I do every time? I multiply by 1/5. If I'm trying to find the sum up through the 10th term, then that means it's S sub 10 for 10 terms. What goes into my formula? I start with the first term, which was 15. Then I have 1 minus the common ratio. The common ratio is 1/5. That would be to the 10th power, all over 1 minus 1/5. I always put my fractions in parentheses. That helps me when I go to do my calculator. So if I type it in, I get 18.7499. I'm going to leave that as a decimal. I'm going to chop it off at 4 places after the decimal. I realize that this keeps going, but the amount I'm adding is getting so small it's not making a big difference. We'll get to more of that later. We'll go through number 9 and 10 and 11. We'll take a look at them in class, so we're going to skip them for now so the video doesn't get too long. And I want to go over to the next page and look at sigma notation. Sigma is a Greek letter. The Greek letter sigma is this capital thing. When I write it by hand, it usually looks like that. It's used to represent sums. To write the sum of a sequence, and here's our sequence, a sub n equals 3n plus 5. We can put that in here inside our sigma, and then we're going to say from n equals 1, we're going to write n equals 1 down here on the bottom, to n equals 1,000. We don't have to write the n again. We can just put 1,000 up on the top. We use this sigma notation, and this is how we write it. So the way we read this is the sum from n equals 1 to 1,000 of 3n plus 5. And what this means is we're going to plug in every number starting down at the bottom with 1 and ending up at the top with 1,000. And what we're plugging them into is our explicit formula. This always has to be explicit. You can't write a recursive formula in this sigma notation. So if we were going to do this, obviously one of our formulas would help here. So let's go through what we would do to do this problem. We would have to recognize, starting in the example, that what we have here is an arithmetic sequence. Sometimes it helps to go ahead and plug some numbers in. So 3 times 1 plus 5, well, that's 8. What would the next term be? 3 times 2 plus 5, well, that's 11. Then I'd have 3 times 3 plus 5, well, that's 14. So I should recognize that this pattern right here is an arithmetic sequence with a common difference of 3, and that's my number out in front. That's like my slope. So I know that I can have this work out. Rather than write out all the terms, I'm going to use this second sum formula because I don't know the last term, and I'm just going to plug into that formula. On the top, I had n going up to 1,000, so that's the total number of terms in the sequence. Then I went to plug in, I had in my formula 2 times a sub 1 being my first term, which I found up there, was 8. Then I had plus n minus 1. Again, n was 1,000 because I had 1,000 terms in my sequence. And then my last was d, the common difference, and I could tell because up here I added 3 each time to get the next term, or because 3 was the slope. So if I just plug in and simplify this, I can work it all out, and I wind up with a big number, 1,506,500. Sometimes our patterns might not be arithmetic or geometric, or sometimes in the second example, what happens is it says expand and find the sum. What does that mean? Expand. It means write out all the terms And find the sum means add them up. So in this case, I need to start with k equal to 3, which means I'm plugging in 3. That's the third term. So I started out and I plugged in k equals 3. Then I plugged in k equals 4. Then I plugged in k equals 5. The last thing up on the top that I was supposed to plug in was a 6. So after I plugged in k equals 6, I stopped. So expanding the series means write it out with the little addition signs in between it. So those are the 4 terms of our series, 15 plus 20 plus 25 plus 30. Then find the sum. The sum means to add them up, and that's the total when you add them together, which is 90. So let's do some examples with this. We'll do some of them and we'll leave some of them for doing in class. Number 12 says, write out and add the terms. And this reads the sum from k equals 4 to 7 of k squared. So I'm going to start out, and my formula is to take k and to square it each time. So every time I'm going to have something squared that's happening. I don't know how many I'm going to have yet. Let's see where I start out. I start out by plugging in k is 4. So the first thing I'm going to do is square 4. Then I'm going to square 5. Then I'm going to square 6. In the last term, I'm going to square 7. I'm going to stop because the last thing I plug in is what's on the top of my sigma. Now I can just simplify this. 4 squared is 16, then 25, then 36, then 49. And last, I could just add them up into a calculator, is 126. All right, that's when I give you the sigma and you evaluate it. The other thing that could happen is I could give you the series, like in number 14, and I could ask you to write it in the summation notation. Summation notation, again, means with the sigma. So I'm going to have a sigma here. Typically, when I'm writing a formula, I'm going to start out with the first term, and then I need to figure out how many terms I want. Well, in this case, my first term is 3, and then I have a second, third, fourth, fifth, sixth, seventh term. So 7 is what's going to go on the top, because from 1 to 7 would give me 7 terms. Then I need an explicit formula to put in here. So I need to figure out what is my pattern. Every time in this one, I'm adding 4 to get to the next term. So I can tell this is an arithmetic series. The formula for an arithmetic series starts with a sub 1. So my first term is 3. Then I have plus n minus 1. I've got to leave the n minus 1 in there. That's what makes it a formula. And then at the end, I multiply by d, the common difference. So you're welcome to leave it like this. They might not write it like this if it were a multiple choice test. It may be simplified, and I could still go from 1 to 7, but if I distributed the 4 and then combined like terms, I would have 4n minus 1, and that's another version of the same notation. To do number 16, I would look each time and say, well, I'm multiplying by 2 every time, so that means that this is a geometric with r equals 2. So again, I'm going to go into sigma. I'm going to start with 1, and I need to count how many terms do I have. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. And then I'm plugging into my formula for geometric. The first term is 1. The common ratio is 2, and that was raised to the n minus 1 power. So that's the formula that's on your formula sheet for a geometric sequence. If I had to evaluate in numbers 18, 19, 20, and 21, on those, I just need to figure out, what do I have? Do I have an arithmetic or do I have a geometric? How many terms? And what am I plugging into? So for example, I would usually start and plug in a term or two to be sure I have the right pattern. If I plug in 1 to this formula, I wind up with 3. If I plug a 2 into the formula, I get 8. If I plug a 3 into the formula, I get 13, and so on. So I can tell, I could also tell because this was linear, that my common difference is 5, which makes this arithmetic. So I know I'm going to use my sum formula. You can use either formula, it doesn't really matter. I'm going to use the 2a sub 1 plus n minus 1 times d formula because I don't know my last term at this point. So I would be plugging in, I have 35 on top of my sigma, so I have 35 terms. So n is 35. A sub 1 I just found was 3. I can plug in, I'd have 35 for n. My common difference I found was 5. And then if I just type that formula into my calculator, I get 3,080 as my sum. We're going to skip the rest for now, and we'll come back and look at them in class. All right, the last bit in the notes here comes to infinite series. An infinite series means it doesn't end. It keeps going forever. We're going to find infinite geometric series, and we're going to find the sum of them. So to find the sum of an infinite geometric series, this is the formula that's on our formula sheet. And it specifies that our common ratio, the absolute value of the common ratio, has to be less than 1. So this means that our common ratio has to be a little number, a number between -1 and 1. So what we're going to say, a series is convergent, or the series converges if it approaches a given number. For a geometric series, this happens only when the common ratio was between -1 and 1, or the absolute value of r was less than 1. In other words, the amount you're adding gets closer and closer to 0. We'll take a look at this in a second. We can also have a series that is what's called divergent, and a series diverges if its sum does not approach a given number. It just keeps growing, or it's not convergent. So let's look at this sort of graphically, how this happens. This is a 2 by 2 meter square. So this thing right here that's a square is 2 meters by 2 meters. If I were to find the area of this square, 2 times 2 is 4, so this is 4 square meters. What I'm going to do is I'm going to start out and I'm going to paint half of the square. So how much did I just paint? I just painted 2 square meters because it was half of my total area. Now I'm going to paint half of the remaining area. So if I paint half of the remaining area, how much did I just paint? Well, half of 2 was 1, so I painted 1 square meter. Now I'm going to again paint half of the remaining area. So if I paint half of the remaining area, I'm now painting a half of a square meter. I'm going to keep going. Now I'm going to paint half of the remaining area. So now I've painted a fourth of a square meter. I'll do this one more time. I'm going to paint half of the remaining area. So now I've painted an eighth of a square meter. Could I keep doing this forever? Yes. I would never finish painting if I always painted half of what I had left. So let's express this pattern as an infinite geometric series. So I started out, the first amount I painted was 2. And then I painted 1. And then I painted a half. And then I painted a fourth. And then I painted an eighth. And to show that this is infinite, I can put a dot, dot, dot on the end to show that it keeps going forever. Now here's the weird thing. Even though I keep painting forever, if I continued, what would the total painted area be? Well, we set up here, the total area of the square was 4 square meters. So I know that if I sum up this series right here, the sum has to equal 4. So let's look at what happens there in our formula. Our formula says an infinite sum. I start out and I plug in on the top of the fraction the first term. So the first term was 2. Then on the bottom, I have 1 minus the common ratio. What did I do every time? I painted half of the remaining area. If I do 2 divided by 1 minus a half, the answer is 4, and that's my infinite sum. The reason this has a sum is because what I'm adding down here in the end is getting so small, it's really not significantly impacting the sum. If I took one of these other things I was doing where they keep getting bigger and bigger, those sums will grow forever and we'll say they're divergent or they diverge. So let's look at just a couple of examples down here. To figure out is the series converges or diverges and find the sum if it converges. So I'm looking at this one and I'm trying to figure out what do I do every time? Every time I multiply by -1/4. So because my common ratio is a little number, or I could tell what I'm adding on the end here is getting closer and closer to 0. This one's going to converge. So it converges. And then I can plug into my infinite sum formula. I have the first term goes on top, 1 minus the common ratio goes on the bottom. So if I do 1 over 1 minus negative a fourth, again, be careful with your parentheses, the answer is 4/5, which is the sum. If I look at number 23, on this one, what am I doing every time? My common ratio is -2. I'm multiplying by -2 every time. If I look at my dot, 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 these are going to keep getting bigger and bigger. They're going to alternate between positive and negative, but still the terms are getting bigger and bigger, and therefore I'm going to diverge. It's not going to have a sum. It won't come to a specific value. If I looked at 24, on this one, I should be able to tell it's going to converge because my common ratio for my formula right here, I was a -1/2, so that tells me it's going to converge. My common ratio has to be between -1 and 1, and then I can just plug into my sum formula. Infinite sum, what goes on top is the first term, which in this case would be 10. If you're unsure, you could go ahead and list out some terms. My common ratio was -1/2. If I do 10 divided by 1 minus -1/2, that will simplify to 20/3. Let me just show you how I'm typing these into my calculator real quick. So I've typed in 10 divided by 1 minus -1/2. I put my fraction in parentheses. I had minus a negative. So that gives me 20/3. If you did this on your TI, you just have to do the math, enter to turn it into a fraction instead of a decimal. Okay, so we'll look at the rest of these in class tomorrow. We'll do some more practice, and let me know if you have any questions. Thanks.